Between 2019 and 2022, 12 early-stage researchers have been part of the Climate Advanced Forecasting of Sub-Seasonal Extremes project, working with different partners all over Europe, from universities and research centers to meteorological agencies and industry. Climate extremes such as heat waves, tropical storms, heavy rainfalls, drought and cold surges exert huge social and economic impact. Some of these events are expected to increase their intensity and frequency with climate change. Reliable information in the sub-seasonal timescale, which goes from about 10 days to 3 months, is of great importance, allowing for early warnings and adequate mitigation strategies.
Forecasting of extreme events at the subseasonal timescale is a very difficult task because some of the physical processes that play a role at that scale are not very well understood due to the inherent complexity of the atmospheric and oceanic system. Researchers in the CAFE project try to contribute to this challenge with new ideas and methods coming from nonlinear physics, complex networks, stochastic processes, and artificial intelligence.
Some of the physical processes and structures that have been investigated at the CAFE project include Rossby wave packets, the Madden-Julian Oscillation, large-scale circulation patterns, and the El Niño phenomenon. The influence of some of these on extreme precipitation events and heat waves has been analyzed in depth. Some parts of the CAFE project aim at fundamental understanding, yet some others have direct applicability in improving the forecasting of extreme events.
Local authorities and agencies have responsibilities at different timescales and require specific forecasts at these time ranges. The Ready, Set, Go approach organizes the process in 3 stages of preparedness. At the ready stage, agencies look at seasonal forecasts to update contingency plans. At the set stage, subseasonal to medium range forecasts come into play to inform of the necessity of preparations. At the go stage, the mitigation actions are ready to be implemented. Forecast reconstruct is positioned in the middle and provides integral information for actions to be taken.
My research interest focused on El Niño Southern Oscillation, ENSO for short. ENSO is a seasonal to interannual climate variation generated through interaction between atmosphere and ocean in the tropical Pacific. When El Niño or La Niña occurs, we hear news from social media more frequently in terms of natural hazards associated with ENSO. When I was a little kid, I had a very deep impression of the severe flooding affecting Yangtze River in China in 1998. And this severe flooding event is associated with El Niño in that year. We create a benchmark method and we proved that this forecast model indeed has a good prediction skill which can extend ENSO's prediction more than 1 year.
In my PhD, I have used a new weather forecast model based on statistical and probabilistic approach to generate ensemble weather forecast. In our first paper, we simulated precipitation across Europe, assuming the relation between past and future weather and using similarities on 70-year atmospheric circulation configurations. We also identified the influence of the high and low pressure on the good or bad forecast. Our method improves the existing techniques by allowing a focus on smaller area and for a longer time in advance. It also has significantly lower computational costs than current methods. Our forecasting tool helps to improve the forecast of precipitation and temperature up to 3-4 weeks in advance at very local scales, which can benefit the agriculture sector, for instance to plan fertilization campaigns or crops rotation, as well as the energy sector management. We already collaborated with a wind farm company in Brazil that explores our model to forecast the wind.
During my PhD, I have co-authored several publications, mainly focusing on extreme precipitation in the Mediterranean. In these works, we used machine learning and other techniques for analyzing a large dataset of the latest 40 years of meteorological data in the region.
Those results can improve extreme rainfall forecasting in the Mediterranean for 2 and 3 weeks in advance, which will help primarily the agriculture sector and emergency response units. We have already collaborated with a research group in Calabria, Italy, that explores the use of our products for flood warning systems. Other such applications are in considerations for location in Greece and Israel. Our core methods are open source, and we can develop custom solutions for specific projects.
The 12 early-stage researchers of the CAFE project have been trained as true interdisciplinary scientists, developing expertise not only in meteorology, but also in nonlinear physics, statistics, and computer science. This has allowed them to contribute with creative novel solutions to the old problem of extreme weather prediction. Some of these results of the project can be of potential interest to many different industries and public agencies.